So hello everybody, it's Joshua Blinkhorn here. This is a video presentation for some joint work between myself, Olaf Beyersdorff and Meena Mahajan. It's hardness characterizations and size width for QBF resolution. So I'm going to be talking about proof complexity and quantified Boolean formulas. But first I just want to say a little bit about solving. So I'm sure many of you are aware about what's been going on in SAT the last couple of decades. But if not, then here's a little summary. So the SAT problem, essentially you're given a CNF, that's a conjunctive normal form formula for propositional logic, and your task is to determine whether it's satisfiable or not. So this was the first problem to be proved NP complete. So the message from theory is that this is the canonical, classically hard problem. But the message from practice is a little bit different. In practice, you have industrial instances which are enormous, hundreds of thousands of clauses, and these SAT solvers are able to solve them. They're pretty efficient. They're used as oracles in larger technologies like QBF solvers, so they're essentially operating as NP oracles. And they serve a whole host of diverse applications. But the message from practice is that this technology is efficient. And this is largely down to conflict-driven clause learning, which is like the state-of-the-art technique in SAT solving. I think it's fair to say that this conflict-driven clause learning, CDCL, is like the heart of modern SAT solving. Now, what's interesting is that this CDCL is closely related to this proof system called resolution. So what's resolution? It's a proof system which operates on CNFs. It's very, very simple. It's just got two rules. So you can introduce a clause from the CNF, and you can make a resolution step over two clauses you've already derived. So the goal here is to derive the empty clause, and in fact, you can derive the empty clause if and only if the CNF you've begun with is unsatisfiable. Okay, so this is a refutational proof system in the sense that it proves the unsatisfiability of CNFs. So what's the connection between CDCL, that's solving, and resolution, that's proofs? Well, actually there's a deeper connection between solving in general and proof complexity in general. And this is as follows. So suppose you have some unsatisfiable formula here. You're going to pass this to your solver. Your solver is going to output some trace and eventually deduce that the formula is unsatisfiable. Now actually this trace can be interpreted as a proof. Right? It's a proof of falsity or unsatisfiability. And, well, this is a proof in some proof system. Now, for example, if this is a SAT solver, this proof system is probably resolution or some variant of resolution. Now this picture is very, very useful because we can use proof complexity, so what we might know about the complexity of proofs, to actually talk about consumption of computational resources over here, right, which is very important. So, for example, if we have some lower bounds in this proof system over here, that's going to specify hard problems for this solver. All right, so the whole idea is that proof complexity can be used as a kind of analytical toolkit for solving. Right? And this works independently of what it is that you're solving. Okay, that's pretty much all I'll say about solving, I think. The rest of the talk I'll be focusing on proof complexity and, in particular, quantified Boolean formulas. So I should say, what is a QBF? It's a quantifier prefix plus a CNF matrix. So here we have a CNF matrix. It's a CNF formula, which traditionally is referred to as the matrix. And here's a quantifier prefix, where a bunch of variables are quantified either existentially or universally. Now a QBF is either true or false because, all the variables appearing in this CNF here are quantified. And the addition of this universal quantification gives us succinct, should we say, natural problem encodings, right? Things which might be difficult to encode just in propositional logic. Well, you add some universal quantification and you get something which is manageable. So here's a very basic, fundamental QBF proof system. It's called QU resolution. And we get this proof system just by adding one rule to resolution. So you'll see the first two rules here are just resolution. And this third rule here is called universal reduction. So what can this do? Well, if you've got a clause which is C or U, then I can drop this literal U, provided that, well, it's universally quantified, and also that it's quantified after everything else that appears in C. Right, so this literal here must be quantified after all the other literals appearing in the clause, and if so, you can drop it. So here's a very simple example of how this works. I've got a QBF here. For all U, there exists X, a couple of clauses. Due to the axiom rule, we introduce these clauses. Then we're going to resolve over the X. So we're just going to get U here on its own in a clause. And then we can apply universal reduction to reduce the U, and we get the empty clause. And that's the end of the refutation. Now, just to point out, you couldn't have reduced U here, right? Because this X is in the clause, right? And X is quantified after U. But you can reduce U here because, it is quantified after everything else in the clause because there's nothing else in the clause. All right, so the point is that you can get this QU resolution system just by adding to resolution this universal reduction rule. And in fact, this is a general thing, this universal reduction. You can do it with a general propositional proof system. Right, so I just showed you how it works with resolution, but it works really with any line-based propositional proof system. So let's fix a propositional proof system P, some QBF phi, and let's see how this works. So suppose you have some line which is reachable in P, and it contains this universal U, right, where U has the highest quantifier level. That means U is quantified after everything else which appears in this F. What universal reduction allows you to do is to assign this U. So you can assign it either 0 or you can assign it 1. All right? Now if you add this universal reduction to your P, then you get this proof system that we're going to call QP. And in fact, provided that P is sound and complete proof system propositionally, this QP is always sound and complete for QBF. Right, so the message is that this universal reduction is giving you a uniform way to turn a propositional proof system P into a QBF proof system QP. Right? That's modulo some very natural conditions on P. Right, so universal reduction is general, and in particular, for example, if we take P to be resolution, then QP is just Q resolution, which I showed you on the previous slide there. So this is all nice. We can generate all of these QBF proof systems from propositional proof systems, but there's something that we want to avoid, and that's propositional hardness. So the thing is, if we have something which is hard for P, so we have some propositional lower bound here, this phi of n, then all we need to do is quantify everything existentially, and we get a lower bound for Q sub P. Right, because there are no universal variables here, so all QP can do on this is what P can do on this. Right, but this is just propositional hardness. Right, this is hardness from the system P. That's not really what we want. It's not really what we want to look at. We're more interested in genuine QBF hardness. All right, so what's left after you remove the hardness from P? So it turns out that in QP we can just really count the number of for all reduction steps. Right? That gives us a measure of proof size, which removes any form of hardness coming from resolution. And in fact, this can be modeled precisely in a very neat and tidy way by allowing an NP oracle in your QBF proof. Right, so how does this work? So we have QBF systems now with NP oracles. So we get this system which I'm going to call QP-NP. All right, and this system has the rules of P. It has universal reduction, and then it has this oracle rule, which allows you to essentially derive anything which is propositionally entailed by what you've already got. All right. So it's essentially allowing you to collapse arbitrary derivations from P into a single step, right? That's the idea. And it's something rather like using SAT calls in QBF solving. That's also true. So I mentioned earlier QBF solvers often use SAT solvers as an oracle. And here you've essentially got an oracle in your proof system which allows you to collapse any propositional derivation in there to just a single step. So you can see that this naturally removes the propositional hardness from the system you're dealing with. So that's the idea. You have these oracles which eliminate the hardness, and then the question is, what sources of hardness remain after you've gotten rid of the propositional one? Right? What's left? And the answer, which is what we're going to be talking about today, is that what's left are circuit complexity lower bounds. That's the idea. All right, so here's just a brief interlude. So here we have the proof complexity theme song. So this begins with a verse on resolution, and it goes on until we get to this couplet here. It says, though bounds for circuits play a role, well, you know, this connection isn't well defined. All right, so what does this mean in the proof complexity theme song? Well, there's a general belief, we say in the proof complexity community, that there's a connection between lower bounds for proof systems which work on some circuit class C, right, and lower bounds for that class. Right? It seems like a natural thing to think about. Right? You have this proof system which is line-based, and all the lines are circuits from this class C. You want to prove some lower bounds on that proof system. Well, it seems like it may well be related to lower bounds for circuits in that class. However, this hasn't been made formal yet in the propositional world. However, in the QBF world, there are some pretty tight, there's a theorem, a very tight correspondence between QBF proof complexity and circuit complexity. And it's this theorem here. So the theorem says that there exist hard formulas in Q Frege. So Frege here is a propositional proof system, a class of propositional proof systems, which are kind of your standard textbook systems. So we have hard formulas in Q Frege if and only if there exist lower bounds for Frege itself, which is one of the, probably the major open problem in propositional proof complexity, or you have lower bounds for non-uniform NC1. So more precisely, P space is not a subset of NC1. This is another major open problem in circuit complexity. So you see this unites propositional proof complexity, circuit complexity, and QBF proof complexity. So here's an alternative formulation of this theorem, that you have superpolynomial lower bounds for this Q Frege with an NP oracle, if and only if P space is a subset of NC1. All right, so here we've just used the NP oracle to remove the case which corresponds to propositional hardness. Right? So we have this nice theorem statement. And in fact, there's a similar theorem, superpolynomial lower bounds for Q extended Frege with an NP oracle, if and only if P space is a subset of P poly. So this is all very nice, but it doesn't tell us anything about resolution. And that leads us nicely to the following question. Can we characterize QBF resolution hardness by circuit complexity in a similar fashion? All right, this is an interesting case because QBF resolution corresponds to what's going on in QBF solving. So we were able to answer this question affirmatively. Yes, we obtain a tight characterization of QBF resolution by a circuit model which is a form of decision lists. Now, using this characterization, actually, we obtain a size-width relation for QBF resolution. So I'll talk a little bit about what size-width is shortly. And this relation gives rise to a lower bound technique, which allows us to unify and generalize previous lower bound approaches that have been used for QBF resolution. So in many cases, this gives rise to much simpler lower bounds than, or proofs, much simpler proofs of the lower bounds themselves. All right, so now just a little bit about our circuit model. What is a unified decision list? Well, it's a natural generalization of standard decision lists to multiple outputs. So it computes functions which are from n-bit vectors and goes to m-bit vectors. Right? So the traditional model m equals 1, so it's just outputting bits. Here we're outputting a vector of n bits. So let's imagine the input variables are these x's and the outputs are these u's. Essentially what you have is just a list of if statements. If each if statement queries some term, that's the t. These are terms in the input variables. And if that term holds under your assignment, then you output the corresponding b. So you set your output variables to the corresponding b vector. All right, so you just go through the list. You find the first term that hits. This might be tk, right? Then you output bk. All right, the final line has no term, just to make sure that it does indeed compute a function on the whole domain. So it's a very, very simple model, and we call this unified decision lists, or UDL for short. Now, actually, UDLs give us a way of computing counter models for false QBFs. So what does that mean? All right, so suppose you've got this QBF here, this phi, existential variables the x's, universal variables u, and suppose we have a UDL, t, which has inputs x and outputs u. So we're going to call t a UDL for phi if, for each assignment to the inputs, some alpha, if you take alpha with its corresponding output from the UDL, that's t of alpha, this falsifies the matrix of the QBF. Right? So you take the input, you hit the UDL, this gives you an output, and the input and the output together should falsify the matrix of your QBF. Additionally, the UDL needs to respect the quantifier dependencies of phi. Right? So for example, if your prefix is exists x1 for all u1 exists x2, then the value of u1 must only depend on x1. Right? It can't depend on x2 because that's quantified afterwards. Provided your UDL satisfies these two conditions, then we call it a UDL for phi. And this is what we can prove, our characterization theorem. Let phi be a false QBF of bounded quantifier complexity. Bounded quantifier complexity, this means that the number of alternations between existential and universal quantification is bounded. So the number of alternations is bounded, let's say, by a constant. Then the size of the smallest QU resolution refutation, even with an NP oracle, is polynomially related to the size of the smallest UDL for that QBF. Right, so there's a polynomial equivalence between the size of the smallest UDL and the size of the smallest QU resolution refutation with an NP oracle, provided that the QBF is bounded. So that's the characterization. Equivalently, you could say, well, a sequence phi of n of bounded quantification is hard for Q resolution if and only if either the formulas require large unified decision lists, or two, the formulas contain some kind of propositional resolution hardness. And so here we have these two distinct reasons for hardness, and actually the propositional reason here can be precisely identified. All right, so from the formula, you can precisely determine what the propositional lower bound is there. All right. So now a little bit about size width. So firstly, what is width? Well, the width of a clause is the number of literals, And then the width of a resolution refutation is the maximal width over its clauses. Right? So the width of a resolution refutation is just like, you look for the widest clause, that's the width. Now, the size-width technique is probably the celebrated technique in propositional proof complexity, and it allows you to prove a size lower bound via a width lower bound. All right, so you've got some formulas. You want to prove that they're hard in resolution, let's say. They require large resolution refutations. What you can do is say, well, look, actually, they require wide resolution refutations. Therefore, they also require large resolution refutations. Right, so the point is that these width bounds are often much easier to prove. And since the width lower bound implies a lower bound, then you reduce your problem to just proving a width lower bound. So that's the idea there. Now, size width for QBF has been investigated based on the original relation from the propositional world. So that's this here. All right, so this is this relation which relates the size and the width in propositional resolution. But actually, this relation here has been completely ruled out for QBF, right? This doesn't hold in the QBF world. The actual proof idea used to prove it doesn't work. And crucially, the counterexamples which show that this relation doesn't hold all use unbounded quantifier alternations. Right, but this could lead you to say, well, size width just doesn't work for QBF at all. Right, but that's not the case. QBF does have some size width relations, and here's one. So we have this relation here, which works for the QE resolution system with an NP oracle. So this looks kind of similar to the original relation, but there are some differences, some crucial differences. And first of all, just to discuss these briefly, we look at existential width, but we ignore the axioms. Right, so in particular, there's no dependency on the initial width of the formula. And you'll notice that there's this d cubed here, moved its way into the denominator, and d is a quantifier alternation of f. All right, so this perhaps explains why the original relations gave us nothing. Right, we need this dependence on quantifier complexity to say something sensible. Of course, as this d gets large, then this relation is not going to give us anything. Okay, so the proof of this relation here uses our UDL characterization, and it also uses a size width result for decision lists due to Bischutti. Okay, so now just a couple of examples before we finish of how we use this relation. So here are some parity formulas. It turns out that the only countermodel for these, actually, the universal variable, computes the parity of the existentials. Now, it's very, very easy to prove a lower bound on these formulas using our size width technique, because it's very easy to see that the first line of a UDL must contain all the existential variables. Otherwise, it doesn't compute parity, and this immediately yields an exponential lower bound. Right, so it's very, very simple. A second example, we have the equality formulas. And these formulas, the only countermodel computes, well, the ui is equal to the xi. So all these u's here have to take the same values as the x's. Now, again, you can see if a UDL computes such a countermodel, its first line has to include all the x's. Because if it doesn't, it's not computing that countermodel. So again, you get the exponential size lower bound here as a direct corollary. All right. So this brings me to some conclusions here. So we obtained a tight characterization of QBF resolution hardness using a circuit model, UDLs. UDLs are some natural circuit class in which you can compute QBF countermodels. It gave rise to size width relation for QBF, but with a different dependence than in the original propositional relations. And using this, we could get some easier proofs of many QBF lower bounds. Also, this technique generalizes and unifies the two main previous lower bound techniques for QBF, which were based on strategy extraction and something called size cost capacity. So I didn't talk too much about how that takes place, but lower bounds from these two techniques can always be shown using the UDL approach. Finally, just an open problem to cite. So wondering what's the right circuit model for unbounded QBFs, given that our technique works just for those which have bounded quantifier alternation. All right, that's everything I wanted to say. So thank you very much for checking out this video, and enjoy the rest of the conference.